Today we are continuing our discussion on forward kinematics. I'm using Professor Alexander's slides here, which I found is one of the best in teaching forward kinematics, and thanks to him. Now here you can see a two-link manipulator, right? And P is the end point of the manipulator, end of the second link. And there is another frame, which is the E frame, end effector frame. Probably this is the tool that you connect to the last link of the manipulator. So the tool has its end point, and that is what is called the tool center point, TCP. So the end of the manipulator and the tool center point are two different points. So therefore they have their own coordinate frames. Now you need to understand the basic principles of assigning coordinate frames. You can see here x1, y1, that is the first coordinate frame, which is attached to the first link. First link is the link L1 over here, length of the link 1. And the frame is at the end. Frame is located at the end of the link. And this is the second link. At the end of the second link, you have the second coordinate frame, that is x2, y2. All right. It is out of the board. So every time, every link has its coordinate frame, which is attached at the end point. So this is one principle in the standard DH representation, right, of the manipulator. So don't forget that. There are other things you need to remember. That is, you start with the joint and then the link. So joint 0, link 0. In fact, there's nothing called joint 0. Joint 1 is the first joint. So you have link 0, which is the ground or the table or the base of where the robot manipulator is actually located, is sitting on. And you have the joint 1 and the link 1. Joint 2, link 2. It goes like that. And this table here is what is called the DH table. And there you can see and the first row is for joint 1. Joint 1 is over here at the origin, right, is the joint 1. Now, if I give you a little recap of what we did last time, because without this, it's extremely difficult for you to understand this mathematics, right? This x0 and y0 is the base coordinate frame. Base is not moving, it is fixed. So you can arbitrarily assign x and y. All what you need to maintain here is that they are orthogonal coordinate frame. X0, y0, they are normal to each other, right? X, y, z is a right angle coordinate frame, right hand coordinate frame. So other than that, you're free to assign it the way you want on the 0 link, base link, okay? And the first link is over here, you can see, and at the end of that, you have the frame, first frame. Now, you have to relate the 0 frame, x0, y0, z0, to the first frame, x1, y1, z1, all right? So, DH representation explains this relationship in 4 steps, 4 steps. You have the displacement, rotation, like that, okay? The first one is the displacement. This coordinate frame, x1, y1, right, with respect to x0, y0, right, the motion along z0, you can see z0 is out of the board, right? And if x1 has come out of the board or it goes into the board by a certain distance along z0, z0 is out of the board, directly out of the board, and that is d1 over here, right? D1 over here. This column, D column, is that displacement. But here, you know, everything is on the surface of the screen, right? X1 does not come out or goes into the board, right? So it is at the same plane with x0. In fact, x0 and x1, they are intersecting at this point. So therefore, there's no distance between them along the z0 axis. So therefore, d is 0 here for the first row, right? The first joint, d is 0. And after that, you need to remember whether x1 has rotated with respect to x0 around z0. Z0 is the z-axis of interest right now. And here you can see Q1 has the angle. So in fact, X1 has rotated by an angle Q1 with respect to X0 around Z0. So therefore, the angle is Q1. So in place of theta, we put Q1. All right, Q1 is the first joint angle. Not only that, and after that, you now figure out Z-axis. Earlier, you try to figure out x-axis. Now z-axis. Now this z0 to z1. Well, z1 is located somewhere here, right? Z1. Z0 is somewhere located here, right? So z0 moves along this length to z1. They're parallel to each other, right? You start off at z0 and moves to z1 along x1. And that distance is called A. In fact, in our diagram, it is L1. So that is why L1 comes over here in place of A, right? The distance. Now, Z1, right? So let's say you start off with Z0. Now it is at Z1 at that position. And then you have to figure out whether there's a angle offset between Z1 and Z0, right? Around X1. And here, both these axes are out of the board, right? Out of the board. They are parallel to each other. So therefore, there's no relative difference in angle in their orientation. So alpha is 0. So if you continue this discussion, right? First, x0 to x1 along z0. Then x0 to x1 around z0. And then z0 to z1 along x1, and then z0 to z1 around x1. Right? It's a displacement, angle, displacement, angle. 4 steps. You can move from x0, y0, z0 to x1, y1, z1. Okay, with these 4 parameters. So now alpha is a rotation, a is a distance, d is a distance, theta is a rotation. So irrespective of the sequence here, you can say you start off with d and theta, then a and alpha. Okay, d theta is the first operation, like rotation and translation, and then a alpha, displacement and rotation, right? So work out that way. Take d and theta first, either way you want, right? You can have the rotation first, translation next, or the other way around, because it's a screw operation, the rotation and displacement with respect to the same axis. So theta and d you can take together, alpha and a you can take together, and make sure you multiply d theta and operation with a alpha operation. Okay, all right, fine. So now you can see over here, if you do that, right, you get to this one, 0, A2, which means the second coordinate frame end of the link with respect to 0 coordinate frame, which is the base, right, is given by this one. So how do you get that? So for that, I can open my MATLAB and show you how it happens. So I already opened MATLAB. You can see it over here, right? So what do we have? We have so again, if I refer to this one, right? You don't have any distance, but there's an angle, right, around z-axis. So if I get that operation, it is basically rot z some angle. So let me give some number, pi over 3 or something like that. Okay. So this is uh, the first two rotation, first rotation and translation. In fact, there's no translation here. Second one, there's a translation by a distance L1. You can see it over here, right? And after that, there's no rotation. So it's simply a translation only, right? So I can write down the translation as trans L, but this is along x-axis, right? So let me give, say, 5 centimeters, right? Comma 0, comma 0. Okay. So that's it. Now, when I combine these two together, right, what do I get? Rotation and then translation, 5, 0, 0. I get this one. Oops. I have to put T rot here because I need to make sure they are 4 by 4. So this is what I get. All right. This is the second frame with respect to, sorry, first frame with respect to frame 0. So I can now align this and align the answer side by side so that you can see it clearly, right? Can you see that? Right. So it is a cosine angle over here, right? And sine angle over here and 0, 0. You can see the arrangement here. Then second column sine, cosine. The first one is negative. You can see that over here. 0, 0, 1, 0, 0, 0, 1, 0. And then the last one, last column here, the distance, where the first frame is located with respect to the 0 frame. Okay. So you have these numbers and then 0 and 1. Can you see that? Right. So it's so simple, right? It's so simple. So um, now, what about the end point? What about the end point? So if you now let's say if you continue from 1 to 2, again you will get the same thing, right? When you multiply, you can get from 0 to 2. That's what is here. I have only concluded the first operation, first row here. I can do the same thing for the second row over here and get another matrix 4 by 4. And when I combine these two together, multiply, I get this one actually. Okay, this format. Now you are at point P. Starting from point 0 over here, point P, right? And this is your representation of point P, this 0A2. This one is the representation of point P. Now you have attached the tool, right? As you can see over here. Now, what do you see? From here to here, we can have another row in the DH table, like I1, 2, and 3, because anyway, it's not a joint of the manipulator, but there is a transformation from end of the manipulator to the tool center point. Okay. So now if you look at that one, the way the tool has been attached to the end effector, you can see X and Y over here, X2, Y2, and then Y, E, Z, D, right? They're not coincident, right? X and X, Y and Y. No, they're not coincident. There is some sort of orientation difference here of the end effector frame with respect to the second frame. Can somebody suggest, propose this orientation as you see it? Any answers, please? How can we describe this orientation of the end effector frame, E frame, with respect to the second frame here? You can see it on screen. Can you see that if you rotate, yeah, go ahead.
So that matrix is already there, the transformation matrix from end effector to the second one.
Yeah, but I want you to suggest. Matrix is there, but physically, can you guys suggest it? How do you get there? The answer is here, 2E transformation, right? But how do you get there if it is not given? And if you are supposed to derive it, how do you do that?
I think we have to first mark the figure out the reference frames. Say
Yeah,
that
so tell me, what are the operations here now? Now, there should be rotations and translations, right? So, what are the rotations here? What are the translations here as you see it? Because you can visually see it, right? Just use your eyes and see it very clearly. What do you see? Now, earlier, you rotated X0, Y0, Z0, that frame, and translated, and eventually put it coincident with X1, Y1, Z1, right? Likewise, here, how do you rotate this X2, Y2, Z2 frame in order to coincide with XE, YE, ZE? Can anybody guess? Right. I can give you the first motion like this. Now I see that if you rotate X2, Y2, right? X2, Y2, this frame, around X2, okay? Now I rotate this around X2 by 90 degrees anti-clockwise. So you're watching from here at the end of the arrow, right? You are turning counterclockwise by 90 degrees, right? When you do that, what happens is that the z-axis, which is out of the board, right? Which is out of the board. So it's like that. It turns like that, right? And align with this ZD direction. And this Y2 axis will come out of the board. Now it is vertically or normally out of the board. Okay. It's a single rotation around x-axis by 90 degrees. So then Z is now on the board, like as you see here, ZD, and y-axis, which was on the board, on the screen, is now normal to the screen, normally outward, right? So then what you do? Can somebody suggest, take it from there and propose the second rotation? What is the second rotation? Now, your Z is aligned probably, right? Your Z axis is aligned. The moment you rotate around X2 axis by 90 degrees, Z axis falls onto the screen. So that is done. But other two axes are not done yet. How can you get the vertical axis, vertically outward axis onto the screen? You have to turn by 90 degrees. Around which axis?
X-axis.
Around Z axis, which is already on the screen. Now this time, is it clockwise or anti-clockwise? This motion, which is now Y is out of the board, and you turn it clockwise so that Y axis falls onto the screen over here. So the second rotation is around Z axis by 90 degrees, and that's negative 90 degrees. Okay. So these are the two rotations. Then you have the orientation adjusted. That's fine, right? First rotation is around X axis by 90 degrees positive. Second rotation is around Z axis by negative 90 degrees, right? After that, what happens? After that, now you are still there at point P. Now you want to get to point TCP, right? So now still you are with respect to frame 2. Still you are with respect to frame 2. Now you move with respect to the rotated axis. Remember that. All of these motions are with respect to rotating axis, right? You are still at frame 2, but your like on the fly coordinate frame of reference is what you have at the moment, the present coordinate frame. So it is actually this frame now, ZD, XE, YE, but not in this position, but at point P, at point P. Now, with respect to this new frame, newly rotated frame, right, in this maroon color, you have to move from point P to this point, TCP. And it is clearly a displacement along Z-axis and along Y-axis. Some distances, okay? So therefore, I think we can write this entire operation as this. So let me open this notepad, and I would say the first rotation is around X-axis, right, by 90 degrees, right, pi by 2. It's a rotation. Okay, and then I have another rotation around Z-axis by minus pi by 2. And after that, there's a distance, right? Translation, what is that? Along Z-axis, right? How much? Let's say, give some number, 3 centimeters. And along Y-axis, give some number, 2 centimeters. Okay, you have to figure that out, this transformation. You can put as a DH thing on the this table, right? But it's not compulsory. You can work it like that also. So if I open my MATLAB now and try to figure out what is that, right? So it's a T-rot, okay, T-rot X, right, around X-axis by 90 degrees, so pi by 2, right, multiplied by another rotation, right? I can do the 2 rotations first and then the translation. That's also all right. So that is T rot Z. This time it is minus pi by 2 multiplied by axis. So this is translation. Actually, I can do this translation 2 together. right? Z3, Y2, no X. So it is 0 for X, and for Y it is 2, and for Z it is 3. All right. So this is the answer I get. Now, if you look at that one, this answer with the given answer 2TE, and you can see the similarity 0, 0, minus 1, 0, and then 1, 0, 0, 0, 0 minus 1, 0, 0, and 2 minus 3, 0, 1. 2 minus 3, 0, 1. Perfect. So I'm trying to convince you that you don't have to try to remember anything, right? You need to execute what you see. So use your eyes, figure out where the coordinate frames, figure out what are the rotations, what are the translations, right? Okay, so it's that simple. With a very few basic rules in mind, okay, um, you can do this, and it will make your life very easy if you stick to that one. But if you think you can remember things and later frame it, it's not going to be very effective, and you find it very, very frustrating. Okay, so use MATLAB and test it out, and you will see how entertaining that process is. All right. So now you have 0A2 transformation from base to the end of the manipulator and the last link. And then from the last link to the end effector or tool center point, right? Coming as another transformation. Okay. Now, uh, if you combine all these things, 0A1 multiplied by 2 TE, right? They're all 4 by 4 matrices, right? And you can actually get 0A2Q, right? This is the position um, with respect to the 0, tools and point, okay? Now, one thing I want to tell you here is that if you look at this uh, second end of the second link and the tools and point, right? Because of the axes are disoriented, um, your motion along ZE is actually seen by the second frame as a motion along the negative y direction. Okay, because negative y2 and ZE are actually in the same direction. Okay, y2 is this way, Z is that way, but it's the same direction. So your displacement of whatever number of centimeters along ZE direction is now recorded as a negative uh, deflection along y2, right? Y2 this way, but it's the other way. So that's why you got this negative 3 here, right? This is y-axis of frame 2. And also you got a displacement along x direction, but you never moved along x direction, right? You moved along y direction, but ye and x2 are aligned. So therefore, your motion along ye is seen by joint frame 2 as a distance, as a displacement along x2. So this coordinate mapping x to y, z to x like that is already done in the rotation part. So therefore, you don't have to worry about it. You write down the displacements with respect to its own coordinate frame, and then the transformation will adjust it to the other reference coordinate axis. Okay, right. So I have asked you to do that as a homework. How many have done it? I have explained over here using MATLAB. How many have been able to do it? Can you raise your hands those who have done it? Panuka has done it. Anybody else? All right. So this is extremely important. I don't know why others are not interested in, but with a little effort, you can learn this, and it will be a lot of say it's a rewarding experience. By spending little amount of time, you can actually get rid of a lot of frustration later on. Okay, right. Now, there are some ambiguities in defining coordinate frames, right? How do I put, how do I assign frame 2, frame 3, frame 0 like that? Uh, so these are the guidelines for that, right? For example, frame 0. What is frame 0? Frame 0 is the coordinate frame that you attach to the base of the manipulator. All right. Now, base is not moving. Therefore, you can arbitrarily assign it any direction you want. Okay. Now, this freedom of assigning the coordinate frame, you can use it for your advantage. So, what is the advantage here? Now, what is after frame 0? Well, it is frame 1. Okay. Frame 1 is attached to link 1. Link 1 is moving. It moves this way and also that way. So there is a home position for link 1, home position, right? When it is not moved this way or that way, it's home position, right? So if you assign your 0 frame to align or coincident with frame 1 at its home position, you make things very simple and accurate. Okay? So remember that frame 0 is usually assigned to be coincident with frame 1 at its home position. So after that, frame 0 does not move, frame 1 moves. So if there's any rotation or translation, right, frame 1 will be different, okay, not coincident with frame 1 in the motion. So remember that one. And frame n, if you look at frame n, that is the end of the manipulator. ZN axis is not specified. So this is again to tell you that you have a freedom to assign this Z axis the way you want. Okay. Again, use it for your advantage. So what is the advantage here? Try to get some of these axes aligned so that you get rid of some of these rotations and translations. Okay. Right. And also one thing to be noted is that the x-axis, okay, must intersect and be chosen orthogonal to Zn minus 1, right? So the Z-axis of the previous frame and x-axis of the present frame are normal to each other. So you have to maintain that requirement. Remember, from Z0, right, we moved Z0 along x1 so that it eventually went coincident with Z1, Z0 to Z1 along the common perpendicular between these two axes. Z0, Z1, the common perpendicular is x1. Remember that? So therefore, x1 is normal to Z0. So that is this requirement. Then positive direction of Z I minus 1, up, down, on axis of joint I is arbitrary. Again, direction, you can take it vertically upward or vertically downward, right? Arbitrary. And also use it for your advantage to make the kinematic structure as simple as possible. Right. So it goes on. These things, please read and understand, right? All of these things we have already covered in graphics. Let me take another one or two. Say this one. If Z I minus 1 and Z I are parallel. So again, you saw this case earlier. Two consecutive axes are parallel, right? So when they're parallel, the common perpendicular is not unique, right? You can have as many common perpendiculars as you wish. Again, you have the freedom to adjust it, right? In the most appropriate position so that you get rid of some of these parameters that you have to deal with in the DH representation. Okay. Right. Now with that, we can look at some of the existing famous industrial manipulators, right? What you see here is the SCARA robot. I think I have shown you, one of the previous lectures, the SCARA robot, right? So it has three vertical axis rotary joints. Look at the first one, Q1, and the second one, Q2, third one is a linear joint here going up and down and then rotate at the end, right? So let's say this is two rotations, right? And then third one is a linear actuator going up and down, prismatic joint. And at the end, you can rotate, right? Rotate, and it's not a drill or something, right? It's not spinning that fast. Gripper or something you can use to pick up objects like that. So it rotates to the proper direction, right? Before you pick it up. Now, can we assign coordinate frames to this manipulator? So, of course, you can see this gray box here is the base, right? So this should be the base. So it's 0 frame. So assigning coordinate frame to the 0 frame is arbitrary. You can place it anywhere. Huh? So as we described just a while ago, let's look at the first frame and in the home position. So home position of the first frame would be our base coordinate frame. All right. But to illustrate you the process, we will make it slightly differently, right? So that you can see these coordinate frames clearly. If they are coincident, it's difficult to visualize, right? So here you can see the first axis, right? Where link 0 and link 1 are connected, right? This is the first joint. This is the first joint and the axis, joint axis. And this is the second joint and joint axis. This is the third axis going up and down. And at the end, it rotates and it's the same axis. So this translation and rotation are both along and around the same axis. Okay, so that is why you see J3 and J4, the same axis. One is prismatic, the other one is revolute. Now, at very early stage, we can say because of the parallel axis, right? Because the parallel axis here, alpha is 0. Alpha is 0. Twist, link twist is 0. At the lower end and the upper end of the link, right, there's no twist. So this is Z, this is the other Z. If there's a twist in the link, they are misaligned. But here, There's no misalignment, so which means there's no twist in any of these links. So it can be 0 or pi. So depending on your selection of coordinate frames, whether you select, is it up or is it down, right? So if this is up, this is down, again, there's a twist about 180 degrees, okay? So if you have Z and Z both vertically up or vertically down, then alpha is 0. All right, so figure out the axis and the distances. Well, this is the distance from Z0 to Z1, right? Z0 to Z1. This is A1, the first link. And then Z1 to Z2, right, along this direction, A2. And after that, you come to the prismatic joint over here, right? And you figure out A3 equals 0 because you know now the distance from, say, Z2 to Z3, right? In fact, Z1 to Z2 is physically along this direction. You can physically see the distance from here to here. Now, from this point onwards, over here, you have Z2. Okay, along this axis, you have Z2. And along the same axis, you have Z3 as well. Can I go back and show that you? Here, you can see. This is J2. This is J1. At J2, you have Z1. This is Z1 axis. This is Z2 axis and Z3 axis as well. Both Z axis, right? 2 and 3 are coincident like that. So therefore, there's no motion from Z2 to Z3. All right. So therefore, that distance is 0. A3 is 0. Now you can see the frame assignment here, right? I think the first thing I want to pick up is the first coordinate frame, x1, y1, z1, and we locate it over here, right? At the end of link 1. This is link 1. At the end of the link 1, you have the coordinate frame, right? And this is the 0 frame. This is a 0 frame, right? You could have placed it anywhere on this axis because it's arbitrary, right? And by doing that, you could have made d1 to 0. d1 is this displacement, right? X0 moving along Z0, right? A certain distance so that it coincides with this X1. So X0 to X1, the distance vertically upward, right? It's non-zero here, but you could have made it to 0 so that your mathematics would be a bit more easier. But to illustrate, purpose of illustration only, that you have this difference between these two frames along Z-axis. All right. So this is the end of link 1. You have the frame 1. And this is the end of link 2. This is link 2. So you have x2, right? y2 and z2. Z2 is vertically upward. All these z-axis 0, 1, 2 are vertically upwards. This Z3 is also aligned with that one, right? So then you have the displacement, some distance. That's why x3 comes over here, right? From x2 to x3, there's a distance along the same axis. And after that, let's say you attach something to the manipulator and you generate this x4, y4, z4, is additional coordinate frame. Okay. So the robot itself has 4 joints here, right? First joint, second joint, third and fourth joints are here. Third one is prismatic, fourth one is rotary. That's all what the robot has got. So you can see first frame, second frame, third frame, and the 0th frame, right? But now you put this additional gripper or something that you want to connect to the manipulator. We represent that using X4, Y4, and Z4. Right? Now, can you fill the DH table for this manipulator? If you try, you get this table. Right? I've already uploaded this lecture slides to the Moodle page. You can download and work it out, right? And make sure you understand all these things. So let me take again some of these rows, right? And say the first thing is that you have to move x0 to x1, right? X0 to x1 along z0, along this z axis. So eventually what we are going to do is we want to move x0, y0, z0, the 0th frame, we want to move and coincide with x1, y1, z1, first frame. So how do we do that? From 0th frame to the first frame. First, we move upwards along z axis and the distance is d1. So that is why d1 is over here. Very easy. And now you are not anymore here. You are somewhere here, right? And then you want to rotate x0 to x1 by some angle, right? So that is q1. Now you have x0 aligned with x1, looking at the same direction. Now you move along x1 from here to here, right? Your coordinate frame z0, which is vertically upwards, you are moving it along this line of length a1, and that is why a1 is over here. And now you are actually there, the first frame. Only thing is whether there's any disorientation of z-axis, z0 to z1, you have to work out there. But in this particular case, these axes are parallel, so the twist is 0. So that is why alpha is 0. Similarly, now you can move say first frame to the second frame to the third frame to the fourth frame, right? Like over here. You are done. Now pick up anything, any one of these. Let's say, for example, fourth one. How do we fix it? Well, you start with x3. How do you get x3, right? Along z3, right? Along z3. Z3 is z3 and z2 are like on top of each other this way, but you are moving that way, right? It's a negative direction by d4. So that is why d4 is over here, right? With respect to z3. Okay? So this could be negative d4, right? But if you put negative sign numerically, that's all right. And then you rotate around z3. Z3 is like that, upwards, x3 to x4. X3 to x4, right? If it has to be anti-clockwise, positive, and that is q4, right? The angle. And then what you do? You move z3 to z4, but they are coincident, right? They're actually on top of each other. So therefore, there's no motion between them. So it is 0 here. A is 0. And if there's a twist between the two z-axis, z3 and z4, well, yes, one is looking upward, the other one is looking downward. So therefore, there's a twist of 180 degrees. That's why this pi here. Very easy. This is the process you have to apply for any manipulator, frame by frame, right? Then you can fill this pH table. It's a required skill that you know how to draw the DH table given the manipulator like this. And after that, you take, say, row by row. First row, translation, rotation. In MATLAB, you get the coordinate, homogeneous coordinate transformation matrix between, say, 0 and 1, 1 and 2, 2 and 3, 3 and 4. And after that, you get 4 homogeneous transformation matrices. You multiply them together. You relate the fourth frame, this one, x4, y4, z4, with respect to x0, y0, z0. Okay? Then you know this point coordinates, x coordinate, y coordinate, z coordinate of that point, and also this orientation with respect to the frame 0. So for SCARA, these are the homogeneous transformation matrices, 0 and 1, 1 and 2, 2 and 3, 3 and 4. All 4 of them, right? All 4 of them. And the first homogeneous transformation matrix, the variable is theta 1. That is the joint angle of the first joint. Is the only variable, right? All the others are fixed. Like, say, for example, D1 is fixed. And 1 to 2 is homogeneous transformation matrix of frame 2 with respect to frame 1. There, the variable is theta 2, second joint angle. Third joint is a prismatic joint. So the variable is D3. There's no rotation of that frame with respect to previous frame, but there's only vertical motion. So therefore, it is very simple like that. If you look at the first part over here, the top left 3 by 3 matrix, it's a unit matrix, identity matrix. So there's no rotation. And then 3 to 4 is this one, right? There's a distance and also some sort of rotation, okay? So there are 4 variables here, theta 1, theta 2, D3, and theta 4. So when you combine all these things and multiply together, you can generate 0 to 2 by multiplying first 2 homogeneous transformation matrices. And you multiply with the third one, you get 0, A3. And if you continue with the final one, you get 0, A4. Fourth frame with all these joint variables, right? Now we call it Q1, Q2, Q3, Q4. Q1 means theta 1, Q2 means theta 2, Q3 means D3. It's a displacement, you know that. And Q4 is theta 4. So when you multiply, you get this 4 by 4 matrix that you see over here. This is the homogeneous transformation matrix of the fourth frame, excuse me, with respect to the 0 frame. Okay. Now you can actually get the information extracted from this homogeneous transformation matrix. So look at the last column, first 3 elements, right? First 3 elements. Oops. The element over here is the x coordinate, and this one is the y coordinate, and this one is the z coordinate, right? Of the frame 4 origin, the tool center point with respect to the base. Okay. If I pedal back, and these 3 coordinate this one, and this one, right? These are the 3 coordinates x, y, z of this point z4 or fourth frame origin with respect to this point over here, the base coordinate frame. And then the top left 3 by 3 matrix over here right? You have the, uh, oops. This is the orientation. So how frame 4 has disoriented with respect to base coordinate frame, right? So that is given over here in terms of three vectors. The first vector is um, the normal vector, sliding vector, and approach vector, or in some sort of orientation. So we can get back to that in a while. Okay, so this is again the same information. Now you can see 0A4, right? And the information extracted from here, Px, Py, Pz, and alpha Z. The positions and rotation, right? So here you can see the three coordinates that we saw earlier, and below that is the rotation, Q1, Q2, and Q4. So as you can see over here, right, the rotation of the fourth frame here, right, is coming from the first joint, second joint, and fourth joint, because third joint is a prismatic joint. There's no rotation there. But all the other three angles, right, that is theta 1, theta 2, and theta 4, or Q1, Q2, Q4, are with respect to the vertical axis here. Therefore, you simply add them together. So positive, negative cancel out. Yeah, your rotation is basically simple algebraic sum of the three joint angles. Okay, like this. All right. Now we have another manipulator here, Stanford Scheinman arm. We call it Stanford arm. It is a 6 degree of freedom manipulator. Well, the Skara one that you saw a while ago had 4 joints, and this has 6 joints, right? But you can see all of the axes here, right? Frames, and you can figure out what is alpha A, theta D. You can fill the DH table looking at the manipulator kinematic structure. So this is the DH table of the Stanford Scheinman arm, right? Please study this at home. Make sure whether all of these numbers are correct, because this Professor Alessandro's numbers, check whether they are all correct. I hope they are correct. And if there's any difference, let me know next time, right? So that we can look at it in detail. So again, now you can understand, no matter how complex the manipulator is, how many degrees of freedom it has, right? It's a very simple step-by-step process. You first figure out the joints, joint axis, and then you place the coordinate frames, and you figure out the 4 parameters for each joint transformation. And then you write the homogeneous transformation matrix for each joint, and you then multiply them in a sequence. You get the endpoint, position, and orientation with respect to the base. Okay, so that's the same process for any manipulator. Here's another one, KUKA LWR4 plus. You can see a lot of other manipulators. This is a KUKA KR5 R650 manipulator. Again, you can see the joints here. First joint, second joint, third joint, and fourth, fifth, sixth. They are coincident at the end point. Again, the same principle. Figure out the joint axis, place the coordinate frames, identify the DH parameters, 4 parameters, and fill the DH table. Now, is this DH table, this convention, the one and only or unique to forward kinematics? The answer is no. You can come up with a different procedure altogether, right? But what had already been presented in, I think, late 50s or early 60s is so elegant, simple, and accurate. So therefore, world over, in the robotics community, they use it. But for various other reasons, certain modifications have been suggested in the recent times. One is the Craig convention. Craig convention is slightly different to the standard DH convention. I'm just showing it to you here, but I don't want you to get confused with it. So therefore, this is only for information, right? But we are not going to do anything with the modified DH convention. All right. So if you look, when you refer to the textbooks, if it is not the standard DH representation, you got to be very careful, right? Your equations and their equations will not give the same answer. All right. So I think that's it for the this unit of forward kinematics. I will upload an assignment on this so that you can work it out. Probably Puma 560, this one DH table, to code it for forward kinematics. Then you can put some numbers in, then you can get the endpoint position and orientation calculated, right? So I'll upload that to the model. Questions, please.